recording, and hope everything will be fine. Okay, so last time I did two things, right? Basically, I showed you that the geodesic equation reduces to the Newtonian gravity in what's called the weak field limit. We will get back to this weak field limit down the line. If we take the next term in the weak field limit, we end up getting the gravitational waves, but we'll do that over time. Right now, I showed you that you do get the Newtonian potential. And then we started a particularly important subject, which is defining vectors and tensors in curved space-time. And the idea is that if we have to accept the idea that the presence of gravity takes the simple Euclidean space-time and curves it in some way, then we must somehow find a way of doing physics, i.e. making some physical equations and writing them and solving them beyond the single equation that we learn, right, the geodesic equation, in curved space-time. So vectors and tensors in curved space-time. And the question is, how do we write equations which will be valid and true in any curved space-time? And essentially, the big motivation that we have is to write an equation which will describe how the existence of mass or energy acts to curve the space-time itself. And that's called the Einstein's field equation. Of course, this is the answer to that. And we will derive this equation. And after that, we will derive solutions to this equation. So this is the big motivation. For that, we use the principle of general covariance. Which states that if we have an equation that we know that it describes the law of physics in flat space-time, normally such a physical equation, when you think of it, is always written as a set of partial derivatives. And we know that this equation preserves its form. So, it looks the same in the presence of gravity, then we know that it is true. This is called the principle of general covariance, right? So let's, if an equation describes the law of physics or a law of physics in flat space-time, and it conserves its form, in the presence of gravity, it should say it preserves its form under general coordinate transformation. Right. Not necessarily from one inertial coordinate system to another, but in general, right? General coordinate transformation x to x prime, then it is true in the presence of any arbitrary gravitational field. And in fact, this follows directly from the principle of equivalence, which we've learned, right? And then the simple proof is look at the second condition, says, okay, the equation assumes to conserve its form, right? So if it's true in one coordinate system, it's true in any other coordinate system. And then from the principle of equivalence, wherever we are in any arbitrary gravitational field, we can always find, always direct, right, a locally inertial coordinate system. So a coordinate system in which the laws of special relativity hold. And according to the first prescription, the first point, the equation holds, it truly describes the laws of physics in that system. So it must hold in any general coordinate system. And the correct way of thinking of this principle is that the laws of physics are independent on coordinates. Right? This is the other way of thinking of all that, is that the laws of physics are coordinate independent. Which otherwise, you can take out all the physics and just throw it away, basically, right? Remember, the coordinate is something that we, the observer, define for our purpose, because we want to have a way of describing the system, right? To tell ourselves. But from the point of view of the system, it doesn't care whether, what coordinate we're using, right? If a particle decays into two other particles, it doesn't need the coordinate it will happen regardless of which coordinate we choose. Right. Otherwise, you can take out all the laws of physics and go find something else to do. So this law, especially this part, right, conserves its form under general coordinate transformation. This is really why I insisted on writing down all the laws of special relativity in terms of vectors and tensors, because vectors and tensors are something that I know how to transform from one coordinate system to another. So I can set up, and I know that the form of an equation, which is written in a vectorial form, would remain, at least in special relativity. Now things are getting more subtle, because now we're working not in flat space-time, but in curved space-time. So we need to be careful about things such as derivatives, right, which are absolutely essential in writing any equation in physics, right? How do we write derivatives, for example, in curved spaces? Right, derivative is a change of a quantity, right? So I have to be careful, because what I said, it's not that easy to write a derivative, for example, because if I said that all the vectors belong to a single point in space-time, right? And a derivative meaning I'm taking the difference between the value of quantity at one point and another point. How can I take a difference of two quantities which do not even belong to the same space, right? So that's what we're trying to address right now. So the first thing, which I was trying to emphasize, is that in curved spacetime, I'm going to identify vectors as directional derivatives. So what we're doing the next thing we did basically is generalization of the definition of vectors and tensors to curved space-time. And the most important, which is, although it's quite subtle, but pay attention, right? It's that vectors are directional derivatives. just occurred to me that you might not have encountered this concept before. It is directional derivative is a generalization of the concept of a partial derivative, right? What is a partial derivative, right? I'm taking, I have a coordinate system, right? And I have a quantity, which is defined everywhere, right? There is an f, point x. This is a point of x plus delta x, right? And this is a point of x and y, sorry, and y, right? And this is a point x and y plus delta y. And the function f is defined everywhere, right? And a partial derivative, meaning what? That I'm changing f along the direction of one of the coordinates while keeping the other coordinates fixed, right? So df over the x, right, is just f of x plus delta x minus f of x divided by delta x, and taking the limit where delta x goes to 0. And the y and all other parameters are fixed. Right, this is the direction, this is the partial derivative of f with respect to coordinate x, right? Directional derivative is a generalization of that because I'm taking the change of f along a certain direction, which is not necessarily specified by the coordinates, because in order to define the partial derivative of f with respect to x, I had to define first what is x. I had to put a set of coordinates first, saying, okay, right, this is x, this is y. Before I do that, I cannot tell you what is the directional derivative, the partial derivative of f with respect to x. Right, make sense? Yes, no? So a directional derivative is a generalization of this concept, but I want to do it in a way which does not require me to specify coordinates. Right? Here is how it's being done, right? The main problem that I'm facing was that I insisted on the fact that all the vectors belong to a single point. This was the main issue, right? Because I told you all the vectors, they belong to a point. So the mathematical way of doing it and doing it properly is the following. The first thing which I did was defining a manifold. I did not give you the exact mathematical definition because it's a bit, there are a lot of subtleties there, but I gave you the correct intuition of things, how things do work. So a manifold M, right, it's an n-dimensional space that near any of its point, it resembles an n-dimensional Euclidean space, right? A manifold, right? It's an n-dimensional space. That's near any of its points resembles an n-dimensional Euclidean space. So locally it is Euclidean, but globally it is not. The same as the surface of the Earth, locally is flat, but globally it is not. So a sphere is a classical example of a manifold. Right? It's denoted by M. So one example is a sphere, this is a manifold. Another is a bagel, a torus, right? That's another manifold, right? And the exact name is genus 0, genus 1. It doesn't really matter for our purposes. We're not going to make use of that, right? A porcupine is not a manifold, right? A space which looks like that, this is not a manifold, right? This is not a manifold, okay? It's not, okay? A porcupine is not a manifold. Anything that looks smooth, right? We don't want to get into the mathematical imagination. Okay, we're doing physics. Okay, now after we define, is it clear to everybody what is a manifold? On everything I said so far, any questions so far? No questions? Really no questions? Really? Okay, then the next is to define vectors. And I want to define the vectors in the curved space. And the crucial thing is that I want to do it without leaving the space. I want to stay within the space. I'm not getting out of the space. Okay. We said vectors, they belong to the tangent space. But what do I mean by the tangent space, right? I want to do things in an ordered way, which will not be or won't jump logically. So here's how we do it, right? So we take a manifold M. So it's whatever dimension, right? And I specify a point P on that manifold. Now I can look at all the curves in that manifold that go through P. Right, so this is a curve in that manifold that goes through P. Right. Now, so I can call this curve, let's say, gamma. Right. But I'm using a parameter to specify where I am along this curve. So, you want to catch me, right? Where are you? I'm at lambda. Lambda is the parameter along the curve, right? Lambda equal to 1, 2, 3, 4, n, right? It's a parameter along the curve. Right? I can think of another curve. Well, this is another curve, but it also goes through P. And there will be another parameter along this other curve. It can be sigma. I don't know how to call these curves, so I'm not calling it anyway. Now, if you think of it for a second from a mathematical point of view, right? A curve defines a map, a parameterized curve defines a map from R to M. So gamma, I would say that mathematically, gamma defines a map from R to M, right? R is just a number, right? Lambda. This is via this lambda parameter, right? So lambda equal to 0, meaning that I'm in this point here. Lambda equal to 1 means that so this is lambda equal to 0. So if you say, okay, I'm along this curve, and I'm now at lambda equal to 5, then you know that where I am. I just specified. I gave you a number R, and I specified a location on M. In that sense, this is a mapping, right? So any curve, mathematically, the curves defines a map gamma R to M. Parameterized curve. I'm going to play this game of mapping because that's the way I have to do it in order to avoid using terms that are outside of the manifold. So far, so good? Okay. Now, right, now we already discussed the concept of tangent vectors to a curve, right? But we want to specify what is a vector, right? Without specifying exactly what is a tangent vector to a curve, because we don't know what is a vector yet. So there is a bit subtle here. Right. So far, the only thing we know is that at P, we would be able to form a tangent space at P. How do we do that? So let me do it again. I'm going to copy that. So the next step, the second attempt, I would say, Copy, paste. So the second attempt that I can have, right, is assume that I do have some coordinate system in the vicinity of the point P. Now I can always have that, because if I look close enough at P, because M is a manifold, then it looks Euclidean. And in Euclidean space, I can set the form of coordinates, right? There is no problem. So, I can put myself a set of coordinates, right? Right, which I call X mu. And now I can look again at this curve that I have, right? This curve lambda. And I can say that this curve lambda, right, specifies a mapping, right, from the coordinate to Rn, right, which is just, the X mu to the lambda, right? So a curve given a set of coordinates, X mu, a curve gamma, right, defines a map, right, from M into Rn by giving a set of real numbers. Right? How much the coordinates change when I go from P to along this curve. So that's not bad. I specify the mapping from M to Rn. Essentially what the vector would do. But this is not what I want, because this is coordinate dependent, right? I had to specify the coordinate X mu first, right? So the approach is good. We're making a progress, but we need to be even more general than this. Okay, so this was my second attempt. Now let's look at my third attempt, which is to do it without using any coordinates. So let's see. No. Okay. Right. So again, this is my third approach. Now I simply think of a set of all functions, right, f from M to R, right, from the manifold M to R. So again, in the vicinity of the point P, I think a set of all functions f from M to R. General, right? The set of all these functions is a space, right, which I call it capital F. So this is a space of all mass functions. We said F, we specified, we said that F is a C infinity. So that means it's infinitely derivative. It's well-behaved functions. It's called the C infinity. Infinite derivatives you can find. right? So I'm not trying to get into all sorts of להתחכם. I'm not trying to be too smart. And now I can think of the curve as really being an operator, right? In the same sense that the curve here specified, right, a mapping from the coordinate. Now I'm thinking of the curve to be an operator, right? So the curve, each curve is an operator on this space. Remember, what does an operator do? An operator takes one function and turns it into another function. Right? The same way that a function takes one number and turns it into another number, an operator takes one function and turns it into another function. Right? What is this operator? It takes any function f and maps it into what?
A real number.
No.
No.
No, that's not an operator. That's a functional. What is an operator? Take one function, turns it into another function. So the original function was f, and the new function is df d lambda. It's true for any function. Well, this is the correct mathematical way of doing that. Now, the claim is that the tangent space TP is identified with the space of all directional derivative operators along each curve that passes through P. The tangent space TP can be identified with the space of directional derivatives operators along curves through P. Right. So we're basically looking at the space of all directional derivatives, right? So again, directional derivative is a derivative in the direction of a curve. So it is a generalization of the partial derivative. The partial derivative is a derivative in the direction specified by one of the coordinates. Here is specified by curves in general. So it's really, it's just, again, remember my point. I'm making something in a coordinate independent way. Right? So the fact that this is a vector space is pretty straightforward, right? What do you need to do for a vector space, right? You need to be able to multiply it by scalar, which you can. You need to be able to add them, which you can. Right? And you need to check that it closes, right? So A d over d lambda is another directional derivative, right? A d over d lambda plus B d over d sigma is another directional derivative. Right? So if this is a vector, this is also a vector. This is also a vector. The only thing is left to check that this closes, right? But this is, if you think of it for a second, this is what gives you the Leibniz rule, right? So it obeys the product rule. Well, right. So if we take this new operation or operator, right, a d over d lambda plus b d over d eta, let's say, right, and it acts on two functions, f and g, right, you get exactly what you'd expect to get. A f d g over d lambda plus a g df over d lambda plus bf dg over d eta plus bg df over d eta, which is just a df over d lambda plus b df over d eta times g plus a dg over d lambda plus b df dg over d eta times f, right? Both f and g are some smooth functions which can be defined on the manifold, right? So the new operator, right, is indeed a derivative operator, which is what we want, right? It's a bit subtle, but that's what it is. So this is a vector space, but can we identify this vector space? So this proves that d over d lambda, right, is a vector space, right? But now we just want to make sure that this vector space is indeed the tangent vector space, right? Is it the tangent vector space? Right. So of course, yes, otherwise I wouldn't spend your time doing that over and over again, right? So the simplest way is, of course, to find a basis for this space. So let's find the basis. So the answer is, of course, yes. Find the basis, and the basis, just put some coordinate system as you wish, and then look at the partial derivatives along this coordinate system. So if I put the point P, again, this will be my point P. Now I can put some coordinate system, some coordinate system of my wish. So it can be, no. Right. X1 and X2. And so like this here would be D1, right, D over dx1. This here is D2. D over dx2. Right. And then I argue that this set of directional derivatives along these coordinates, provide a naturally, n vectors which are the basis of any directional derivative, right, along curve, right? So d mu, right, can form a basis for the tangent space. Right, TP. Right. And what I mean by a basis, that means that any directional derivative I can write as sum of some scalars multiplying these basis vectors. Right. That's the meaning of a basis. But of course, this is just what we're going to get is the simple expressions of the components of a tangent vector. Right. So any curve, if again now we're looking at the curve that goes through P, it's specified by lambda. Right. This is a curve, and I'm looking again at the function f from M to R. Right. So lambda To be mathematically precise, I call the curve gamma, and then lambda is a parameter along the curve. Then if I'm looking at the vector d over d lambda, which operates on the function f, right? It's just the limit of epsilon goes to 0 of f of x mu at lambda plus epsilon minus f of x mu of lambda divided by epsilon, which is just the the x mu over the lambda times the mu f, which I just specified. Since this is true for any function f, I just wrote down that d over the lambda is just dx mu over the lambda times d mu. This is my vector, which I wrote as some number, which are the components, times the basis vector, right? Some scalar. Which means that d mu, so the set of all n vectors d mu represent the basis for TP. The partials d mu would represent a good basis for the vector space of directional derivatives. Which again, when you think of it for a second, it makes perfect sense. Of course, the vector, the specific vector, which is represented by d over d lambda, it's just the tangent vector to the curve. So this is just a generalization, right, of what we did in special relativity when we argued that this part here is just a component of a vector on a given basis, which it really is. Now the set d mu, right? I can also call it like e mu is also called d mu, right? This is known as the coordinate basis. Now, note that it is general. I did not ask that these coordinates be orthonormal to each other. They don't have to be orthogonal, right? They don't have to be normalized to unity, right? It's fine. They just have to be a set of n independent vectors. That means that we can choose any other set of basis vectors, which will be perfectly fine. Yeah. Sometimes, of course, we prefer to have orthonormal basis. It just makes our life easier, but it doesn't have to be like that. So this is known as the coordinate basis. Right? It's simply a basis that we chose by putting a set of coordinates in a pretty much arbitrary way. Questions? I've been spending quite some time emphasizing really one point, that I can, in a curved space, I can associate, and I will associate, vectors with the directional derivatives of curves, which go along this space, right? That is quite crucial. to understand. That's why it's worth spending time on it. But it's only this point that I want. Questions? No? Can you hear me though? Just to make sure.
Yes, we can hear you.
Okay. You just don't know what to say. Okay, fine. Of course, you know, guys, it looks very abstract, maybe, I don't know. It may look very abstract at the moment. You're going to see that it ends up exactly what you're familiar with. I'll give you a few examples shortly. Right? You see it. It's actually what you know. You just never called it like that. Possible. Okay. Of course, the important thing in doing it like that is that I'm getting the transformation law of the vectors pretty much for free, right? So if I write down these basis vectors, right? So let's say that I have a new coordinate system. So advantage, the transformation laws of vector components and vectors in general is immediate. Right? Because if I have one basis vector, right? So E mu, B mu is just one basis. So let's say that we're now getting to a new coordinate system. Then we simply use the chain rule, right? D mu prime. Right? Remember, this is D over dx mu prime. Just get this into your head because I'm not going to repeat this, right? I'm just using it automatically. What is that? It's just dx mu over dx mu prime d mu. So to get the transformation law of the vector component, we are doing exactly what we did in special relativity, right? So in special relativity, the basic was the requirement that the vector v is unchanged, right? When we make coordinates, because we said that the vector itself is doesn't care about the coordinates, right? Now the vector v, any vector v, you can write as the component v mu, d mu, right? These are the components, and these are the basis vectors. Right? So since the vector is unchanged by a change of a basis, then we write down v mu d mu is just v mu prime d mu prime. Now we know how the basis vectors transform. So it's just v mu prime dx mu over dx mu prime d mu. Right, so now we just take the inverse of this matrix dx mu over dx mu prime. And so we end up that v mu prime, right, is just dx mu prime over dx mu v mu. I just changed the component. Just show you how the components change when I'm looking at the same vector at a different basis. Again, the only thing that I'm doing here is to require that the vector itself doesn't care about the coordinate. Right. Now, normally, we're not really writing down the basis explicitly. We simply don't need. So yeah, so this is the transformation law of a contravariant vector. Right. And basically any object, this is really what defines contravariant vectors, right? Any object, right, that transforms, or its components transform according to this equation, right? When the coordinates change from x mu to x mu prime is called a contravariant vector. Right? Any object whose transformation law is given by this equation, right, when the coordinate change from x mu to x mu prime is called contravariant vector. So again, the important thing here is that I identified vectors with directional derivatives along curves that go in the manifold. And now, obviously, this transformation law is, of course, completely compatible with the transformation law that we've learned and we've seen in special relativity, right? Because just as a comment, right? So in special relativity, under Lorentz transformation, right? We had that V mu prime is just lambda mu prime mu V mu, right? But the Lorentz transformation is just a specific kind of a coordinate transformation, right? But Lorentz transformation is a specific coordinate transformation. Right? X mu prime is just lambda mu prime mu x mu. So obviously, what we did in special relativity is a specific example of this more general approach. So this is what we did here is more general because it works for any coordinate transformation, not just a simple linear one. Right? Because it's not necessarily linear, it can work for any curved space-time. Now there are a lot of subtleties here, which I'm sure now you're really confused about. I don't know, maybe. Essentially, what we say is that the components of the tensor do not necessarily change when we're changing the coordinates, but they do necessarily change when we're changing the basis in the finite space, right? But here we're using the coordinates to define the basis. So in fact, when we are changing the coordinates, we are necessarily inducing a change of the basis, which then induces a change in the components of the tensor. Right. Again, if we have one basis, right, x new basis, right, then we have a point P, right? We have two vectors, right? So this would be x1, x2. This would be d1, this would be d2. Right? If we're changing now the basis to a new basis, x3 prime. Right? This would be x1 prime, and this would be x2 prime. Point P is not changed. This is P, so now we're going to have the new coordinates would be d1 prime, and then this one would be d2 prime. Right? So when we're changing the coordinates, we're changing really the basis. We're changing the basis, we're changing the components of the vector. Or tensor, of course. Questions? No questions? All the math is clear or you're desperate. I'm just kidding. It's confusing. I agree. It's confusing, but it's not that bad. At the end of the day, I'm putting a lot of emphasis on things which are sort of straightforward in many ways. The only thing that is not straightforward that you need to think a little bit about is the identification that I'm making between vectors and directional derivatives. Okay, but once you accept this idea that when you think of a vector, you're thinking of derivative along a certain direction, which is specified by a certain curve, then everything makes sense. And mathematically, it certainly makes a lot of sense. Okay? No questions? No questions. Remember what I'm doing here, really. Why I'm doing all that. I'm doing all that because I want to specify a way of writing equations in physics in curved space-time. Believe me, I need all that to do that. Okay. Next. Covariant vectors. Let's talk about contravariant vectors. What about covariant vectors? So we got a general definition of a contravariant vector. And we basically continue along the same steps that we did in special relativity, right? So we consider dual vectors, right, which are one forms, and the cotangent space, TP star, right, which is really a set of linear maps from TP to R, right? So the cotangent space TP star is a space of linear maps right, omega TP to R. Again, I don't know, maybe intuitive way of thinking of it is to think of, you know, row vectors versus column vectors, right? So you think of column vectors as some mapping from a row vector into numbers. Of course, in physics, right, the canonical example of one forms is the gradient, right? So the gradient of a function f is df. The canonical example. The gradient of f is a general function, right? Df. Right? So the action of the gradient on the what?
We didn't hear you for a second, for me at least.
I said that the canonical example of a one form, right, is the gradient, right? So you think a gradient of a function f is a general function, df, right? And df that operates, look how I noted it, right? The one form that operates on a vector, d over d lambda, right? Just gives me, the directional derivative of the function f, right? So just df over d lambda. So I see that I put a comment for myself, right? That the function f itself is not a one form, right? And again, the reason is that the one form has to be defined at a point, at a single point, right? And it doesn't care about what happens in other points on the manifold. It doesn't know anything about them. Of course, if you know what is the function at the vicinity of the point P, then you can take the derivative, but we don't want to do that. Right? So we just look at the gradient of the function, which is defined at the point P. So obviously, the natural basis for a covariant, again, it's the same thing. We're just repeating the same game that we played, right? So the gradients, the natural basis for the cotangent space, right, is the gradients of the coordinate functions x mu. So the natural basis for the cotangent space TP star is the gradient of the coordinate function x mu, right? So again, we repeat, it's exactly analog to what we did with special relativity, right? In special relativity, the basis for the cotangent space, right, we denoted it as in special relativity, we denoted it as theta mu, which were defined such that theta mu that operates on the basis vectors of the tangent space, right, is just delta mu, right? And coordinate basis for TP star. Right, and here, of course, we have the x mu as a basis that acts on d mu, so d nu. Well, it's just the d x mu over d x mu, which is just delta mu. So it's the same thing, which means that the set of gradients dx mu, right, provides an appropriate basis for the one forms. Right? An appropriate one. It means that any one form, arbitrary one form W, I can write as W mu dx mu. And of course, the transformation law of the basis of the dual vectors, the one forms, one form, so the dual vector. Right, so the transformation law of the components and then the basis is just using the standard procedure, the transformation law. Right. Of the basis of one forms. Dx mu prime is just dx mu prime over dx mu dx mu. Well, it's for the basis, for the components, exactly the opposite. And omega mu prime is just dx mu over dx mu prime and omega mu. And again, you can argue that every object whose components transform like that equation is a one form or a covariant vector. So this really defines the transformation law of a covariant vector. Right, questions? Any questions? No? Okay, I'll give you an example in a few seconds and see if it's much more resembling the thing that you know than you may be aware of. But of course, it is this is the correct mathematical way which we can use in curved spaces. Now tensors, of course, but the generalization is very straightforward, right? Because we're simply following the same pattern that we did when we talked about special relativity. Right? Simply we're replacing the Lorentz transformation with matrix which represents the more general coordinate transformation. So if we talk about the KL tensor, right, we can expand it it's T mu1 mu k mu1 mu l, and then the basis we use this symbol for exterior derivative, right? B mu1, and then there is an X with a circle in it, right? And B mu K, and sorry, B X mu1, B X mu F. What? This is what's known as the outer product, or tensor product. This is the second name of that. Oh. Basically, it just means that you're acting them one by one, right? You're looking at this vectors, it's acting one by one. Note that the order does matter, right? They're not non-commutative. So under any general coordinate transformation, right? The components change as product of contravariant vectors and covariant vectors. And tensor change by the product of contravariant and covariant. Right? So T mu1 prime, mu k prime, mu1 prime, mu L prime, right? It's just dx mu1 prime over dx mu1, dx mu2 prime to dx mu2, dx mu k prime over dx mu k, right? Times dx mu1 over dx mu1 prime, dx mu L over dx mu L prime, times t mu1 mu k mu1 mu L. Right, simply repeating the same thing we did, just generalizing it. You cannot really get wrong here, because there is nothing here that's, there's nothing else that you can do pretty much. Right. So this is really what defines the transformation law of, well, the components of, but since we're not using the basis anyway, this is the transformation law of tensors. Questions? No? No questions? Okay, now, example. I told you it is much simpler than you think, or that you may think. I don't know what you're thinking here, right? Let's look at the simple, 0-2 tensor, two-dimensional curved space. Consider tensor as and 2D space, forward space, right? And so let's take the coordinate system to be x1 is x and x2 is y. This is the coordinate system. So let's say, the components of the tensor as we knew, right? X0, 0, 1. Now let's change the coordinates. X prime, validate to x to the power 1/3, y prime is e to the power x plus y. If you want to express the 1/3, so now we can specify the old basis x mu in terms of the new basis, right? Express the old basis in terms of the new basis. And so the old basis is x mu, new basis is x mu prime. The x mu to be precise, right? So my x is just x prime cubed. Right, y is just x plus y, just a log. So just a log of y prime minus x, so it's minus x prime cubed. Right? So dx, 3x prime squared dx prime. And dy, right, is 1 over y prime dy prime minus the 3x prime squared dx prime. You just express the old basis, the x mu, in terms of the new basis, the x mu prime. The thing to remember is that the tensor products do not necessarily commute. So in general, dx prime dy prime is not the same as dy prime dx prime. So we have to be careful in what we do, right? So I can write down S, right? S is right. In terms of the new coordinate, right. So I had times x times dx dx plus 1 times dy dy. Okay. Here. Let's see. So dx squared s is just x times dx squared plus 1 times dy squared. So I actually have to open it up. So dx squared is just 9 times x prime to the power 4. And times, I have here dx squared. What did I do? Dx squared times. Oh, okay, because I have to square this dy as well. So I get the 1 from this one plus x prime cube from this one, dx prime squared. And then plus 1 over y prime squared dy prime squared minus 3 x prime squared over y prime dx prime dy prime plus dy prime dx prime. So if I want to express that in matrix form, I'll simply write down as mu prime, right? It's 9x prime to the power 4, 1 plus x prime cube. Here I'll just have a minus 3x prime squared over y prime, and the same here, it's symmetric.
Wait, Asaf, in dy, shouldn't you multiply the 3x prime squared dx prime also?
Yeah, that's the origin of the 1 that I got here. Right, this one.
Ah, okay, okay, sure.
And here, what do I have? 1 over y prime squared. So it's the same thing that you do when you're changing coordinates. Right? Now you can use a transformational directive, you get exactly the same result, of course. Questions? No. No questions. Okay. By the way, I'll give you another problem set today. You have somebody to grade your problem set, which is not me right now. Let's check out on her whether she finished grading problem set number 2. Okay. Again, remember what we're doing. The whole motivation of what we do here is to enable us to write equations in physics in curved spaces, right? In generally curved spaces. And you know, we learned several operations, and many of them are not really affected by the fact that we are moving from flat space to curved space, but there are some things which are affected, and this includes the metric that we saw, the Levi-Civita tensor. We'll go to in a second, and the partial derivatives, which are actually quite crucial. Right? Because pretty much all of the physics equations in physics that we have do include partial derivatives. So let's look at the metric. The first thing is we do is called, this is technically called volume elements in curved space-time and the tensor densities. Okay, the metric tensor G mu nu, right? Beta alpha beta, dx psi alpha over dx mu, dx psi beta over dx mu. That's how we define it, right? So transformation law. G mu prime just eta alpha beta d psi alpha over dx mu prime d psi beta over dx mu prime. Right? I can write it down as eta alpha beta d psi alpha over dx mu over dx mu prime d psi beta over dx nu over dx mu prime. Right? There are three sets of coordinates, so don't mix them. One is the psi alpha and psi beta, one is the x mu and x nu, and the third one is x mu prime and x mu prime. Right? So pay attention, I'm not mixing coordinates. So, you know, this is just this. So we end up with a G mu prime is just G mu nu times dx nu over dx nu prime, dx nu over dx nu prime. So, you know, we're not surprised at all that we discovered that G mu nu is a fully covariant tensor, second one. Of course, the inverse is a fully contravariant tensor. Right? Fully covariant tensor, right? The transformation law of the components of G is exactly what we get for transformation law of 0 to tensor. Right? Hey, say something, be happy. No, the look on your faces. Yeah. Okay. Questions? No?
I have a question.
Yes, please.
You use eta alpha beta, which means the metric of flat space.
Yes.
But you use the coordinate transformation, so G mu nu, G mu prime are the metric of flat space.
No. This was the definition of G mu nu in any space, right?
No.
Eta is indeed the metric tensor in flat space. That is true, of course. This is the definition that I use for G. This is how I define G in the coordinates specified by x nu and x nu. This was the definition.
But we only use the coordinates, not the manifold.
Well, it's a coordinates on the manifold, but yes, remember we said that this is an arbitrary coordinate system.
Yes.
Right?
Yeah.
And we said that the effect of the gravity is to turn the flat space-time into curved space-time. So these coordinates would define a, would be general for any manifold. They do not have to be inertial coordinate system. That's what confuses you.
Okay, I see. Thank you.
The xi's are inertial. They define the simple flat space-time. These are not necessarily inertial coordinates. Now I'm moving from one non-inertial coordinates, mu nu, to another non-inertial coordinates, mu prime and nu prime. Okay?
Okay, thank you.
Okay, so G is a fully covariant tensor, right? What about the G with upper indices?
The same contravariant.
Exactly, this is a fully contravariant tensor. What about the conical delta? How do you call this one?
Oh, it's a 1-1.
Yeah, this is a mixed tensor. This is a 1-1 tensor, that's right. It's called a mixed tensor.
Can I ask a question?
Yes.
If I look at the, for example, in our example, if I if I try to make GA full, the contravariant tensor, if I look at it before the transformation, it's pretty easy to see how I get it. But after I do the transformation, how would I change from covariant to contravariant? It wouldn't be as easy as just doing 1 over the components, right?
The transformations do not change the rank of the tensor, right?
Okay.
Just looking at the component of the tensor in different coordinate system. But if I have a 0-2 tensor, it's not going to turn into a 2-0 tensor, right? I will have to use the metric to do that.
I see. Okay.
Okay. This I'm just talking about. Guys, don't get confused. Okay, I know it's really confusing. I'm just making transformation of coordinates. The whole purpose of what I'm doing, really, I'm generalizing what we did for special relativity for any arbitrary coordinate transformation, not necessarily linear, as we did in special relativity. But you can think of special relativity as a special case, obviously, of what we do here. All right? This is more general. I'm going to need that. You'll see quite shortly why I'm doing all that. But it's just generalization of what we're doing, of what we already did. Now, this looks relatively simple, but not everything is a tensor, right? For example, as we said, the affine connection is not a tensor, right? If it's not a tensor, I cannot use this simple transformation law from one coordinate system to another. I cannot use the straightforward way of transforming it. We'll discuss it. But before that, I want to discuss something else, which is quite important. It will take another 5 minutes of your time. So that's okay, I hope. All right. So another very important example of a non-tensor quantity is the determinant of the metric tensor. So the determinant of the metric tensor right? G is defined as the minus the determinant of G mu or G mu. Why do I put the minus sign? Because I want it to be positive. If I look at eta mu nu flat space, there is a -1 plus +1. So the determinant is a -1. So I put the minus, it's going to be positive. Right? So if I do the transformation of the metric tensor and the determinant, taking the determinant of the transformation of the metric tensor, right? G x mu prime is dx mu prime over dx mu to the power -2 times G of x mu, or G prime is just dx prime over dx -2 times G. Now, this you find in any first year linear algebra textbook, basically. Right? How you take the transformation of the determinant when you're changing coordinate system. Right? Transformation of the matrix under coordinate system change. Now, what is dx prime over dx? How do you call that? If you remember from the linear algebra. Somebody? Please, somebody. No? That's called the Jacobian of the transformation. I see somebody got their faces. You know what is a Jacobian, right? Yeah, you just didn't realize that it's actually useful for something. Well, it actually is useful. This is the Jacobian of the transformation from x to x prime. So, the determinant transforms like a scalar, right? Except for this extra factor of the Jacobian. We have this extra factor of the Jacobian. So that's why it's called a scalar density. The determinant transforms like a scalar plus Jacobian, which is called a scalar density. So it's a special case of a tensor density. Now the number of factors here, the -2 is called the weight. This is the weight of the density. Right? So it says a scalar density of weight -2. Now, why did I take a few minutes of your time telling you all that? Because under a general coordinate transformation, right? Under a general coordinate transformation, right? X to x prime, the volume element, dn x prime, picks up a factor of the Jacobian. Right. dn x prime is just dx mu prime over dx mu dn x. Are you familiar with this formula? Some say yes, and many don't say anything. Are you familiar? Yes, I see that more people say yes. Good. Which means that if I want to get an invariant volume element, what do I do? Right, invariant means that the volume element does not change under the transformation.
You would have to normalize it
How?
by dividing over the Jacobian, no?
Yes. But what does it mean dividing over the Jacobian?
It would be the inverse matrix.
Yeah. So what do I do? Dividing by the Jacobian is just multiplying by square root of the determinant of the metric. Right? So one example and we'll go home. Three D space in spherical coordinate. Right? ds squared. What is an element of length in spherical coordinates? You know that, yeah?
R squared dr.
dr squared.
Oh, sorry, dr squared plus r squared d theta plus d theta squared plus sine squared d phi squared.
Very good. D phi squared. So what is G?
Uh, 1 0 0 0 r squared 0 and 0 r 0 0 r squared sine squared theta.
So what is the determinant of G?
R to the power of 4 sine squared theta, no?
Very good. And what is a volume element? Right? You've seen that, huh? Magic. Looks very abstract, but at the end, we get exactly the same things that you've seen. Only now we are really general. We can do it whatever we want, however we want. Right, guys? There's plenty of cool stuff waiting for you in this course. Okay, any questions before we go home?
I have one about the homework, so if anyone has about the lecture, so I'll wait.
I have one about something in general, but so I'll wait after you.
Yeah. Any questions related to what we said? Guys, I don't need to tell you at this stage, right? Do yourself a big favor. Review this material. Make sure that you understand what's going on here, right? You see how easy it is to get lost. Make sure it doesn't happen to you. Okay? If you have any trouble, if something you don't understand, come and ask. Okay? Do it in a reasonable way, right? I mean, don't say, okay, how did you get to this last equation? But go and see exactly where do you get stuck exactly? What is exactly the problem? But make sure that everything is clear in your head. It's a nice thing about math. It's do it properly. It just takes you from one point to the other along the certain path, and you cannot really avoid it. But it's tricky to get a hold of it. All right. If there are no questions, we'll stop recording.